deep in the constellation Leo, 120 light-years from Earth. A telescope has captured something that will change everything we thought we knew about life in the universe. The James Webb Space Telescope has detected a world where the temperature hovers at exactly 120 degrees Fahrenheit, wrapped in an atmosphere that pulses with the chemical signature of living creatures. Scientists are 99.7% certain they've founded a planet teeming with life, more habitable than Earth itself. We journey to witness humanity's greatest discovery. Prepare yourselves. The data arrived on a Tuesday morning in December, buried in terabytes of infrared light captured by humanity's most powerful eye in space. Niku Madhusudan stared at his computer screen at Cambridge University, watching wavelengths of light that had traveled 120 light-years to reach Earth. What he saw made his hands tremble. There, in the spectrum of light filtered through an alien atmosphere, was a signature that shouldn't exist: dimethyl sulfide, a molecule that on Earth is produced only by living organisms. Not just a trace, but a signal so strong that the odds of it being a mistake were less than 3 in 1,000. The James Webb Space Telescope had found what every scientist had dreamed of: undeniable evidence of life beyond our solar system. The planet, designated K22A18b, orbits a red dwarf star in the habitable zone, where liquid water can exist. But this world is unlike anything in our solar system. 8.6 times more massive than Earth, wrapped in a hydrogen-rich atmosphere that creates a greenhouse effect so perfect that vast oceans remain liquid beneath alien skies. The temperature readings were stunning: 120 degrees Fahrenheit, warm enough for life to flourish, yet cool enough to prevent the complete evaporation of water. Madhusudan's team had been studying this world for months, using JWST's incredible sensitivity to peer through the planet's atmosphere as it passed in front of its star. Each transit revealed new secrets. First came the detection of water vapor, then methane, then carbon dioxide. But dimethyl sulfide was the game changer. A molecule so intimately connected to biological processes that finding it in an alien atmosphere was like discovering a neon sign advertising life. The implications hit him like a physical blow. If confirmed, this discovery would end humanity's cosmic loneliness forever. We would no longer be alone in the universe. The probability calculations were staggering: 99.7% confidence that the signal was real, not noise or contamination. In the world of astronomy, where certainty is rare and discoveries are often overturned, this level of confidence was unprecedented. But K218b wasn't just any world. Its unique characteristics made it potentially more habitable than Earth itself. The hydrogen atmosphere acts like a massive blanket, trapping heat and creating stable conditions across the planet's surface. Unlike Earth's thin nitrogen atmosphere, this thick envelope of hydrogen could support liquid water across a much broader range of temperatures and pressures. The star, K218, is a red dwarf, smaller and cooler than our Sun, but also far more stable. While our Sun will eventually expand into a red giant and destroy all life on Earth, red dwarfs burn for trillions of years, providing stable energy for eons. Any life that evolved on K218b would have virtually unlimited time to develop complexity beyond our imagination. As Madhusudan prepared to share his findings with the world, he realized that December morning would be remembered as the moment everything changed. The moment humanity discovered it was not alone. But this was just the beginning of a story that would reshape our understanding of life, the universe, and our place within it. Scientists once believed we needed to find Earth's twin, a rocky planet orbiting a sun-like star at just the right distance for liquid water. K218b shattered that assumption completely. This world proved that life could emerge in conditions so alien that we never thought to look for them. The planet belongs to a class called super-Earths, worlds larger than our own, but smaller than Neptune. Until recently, astronomers dismissed these planets as inhospitable gas balls, too massive to support life as we know it. K-18b forced scientists to completely reimagine what a habitable world could look like. Its mass creates a surface gravity nearly 3 times stronger than Earth's. A person weighing 150 pounds on Earth would weigh over 400 pounds on K-18b. Yet, this crushing weight might actually benefit life. The intense gravity holds the atmosphere in place, preventing it from bleeding away into space like Mars lost its atmosphere billions of years ago. The atmosphere itself defies everything we thought we knew about habitable worlds. Instead of the oxygen and nitrogen we breathe, K-18b's atmosphere is dominated by hydrogen and helium. On Earth, hydrogen is a trace gas, making up less than 1 part per million of our atmosphere. On K-18b, hydrogen comprises the vast majority of the atmospheric envelope, creating a completely alien environment. This hydrogen atmosphere creates what scientists call a runaway greenhouse effect. But in reverse, instead of cooking the planet like Venus, the hydrogen acts as a perfect insulator, maintaining stable temperatures across the planet's surface. The thick atmosphere redistributes heat so efficiently that even the night side of the planet, which never sees sunlight, remains warm enough for liquid water. The chemical signatures detected by JWST paint a picture of a world where life has not only emerged, but thrived. Alongside the life indicating dimethyl sulfide, the atmosphere contains methane, carbon dioxide, and water vapor, a cocktail of molecules that suggests active biological processes. On Earth, these same gases are produced by everything from bacteria to complex organisms, creating a planetary metabolism that can be detected from space. But perhaps most shocking is what's missing from K-18b's atmosphere: the lack of ammonia, a molecule that would dominate if the planet were a lifeless gas giant. Provides strong evidence that biological processes are actively removing it from the atmosphere. Life is not just present on this world, it's actively shaping its atmospheric chemistry. The discovery of K-18b reveals that the universe might be teeming with life in places we never thought to look. If life can emerge and thrive in the hydrogen-rich atmosphere of a super-Earth, then the number of potentially habitable worlds in our galaxy could be hundreds of times larger than previously estimated. Red dwarf stars like K2-18, which make up 3/4 of all stars in the galaxy, suddenly become prime targets in the search for extraterrestrial life. The implications are staggering. We may not be looking for Earth's twin after all. We may be looking for Earth's strange cousin, thriving in conditions so alien that we're only now beginning to understand them. The James Webb Space Telescope is not just humanity's most powerful space observatory. It's a time machine that peers deeper into the cosmos than any instrument ever built. Floating 1 million miles from Earth at a gravitational balance point called L2 Webb exists in perpetual darkness, its massive sun shield blocking heat and light from our star to keep its instruments colder than the surface of Pluto. The telescope's primary mirror stretches 21 feet across, nearly 3 times wider than Hubble's. But size alone doesn't explain Webb's revolutionary capabilities. The mirror is composed of 18 hexagonal segments, each coated with a microscopic layer of gold that reflects infrared light with unprecedented precision. When these segments work together, they create a mirror so perfectly aligned that it can detect the heat signature of a bumblebee on the moon. Infrared light is invisible to human eyes, but it's the key to detecting life on distant worlds. When planets pass in front of their stars, a tiny fraction of the starlight filters through their atmospheres before reaching Earth. Different molecules absorb specific wavelengths of infrared light, creating unique fingerprints that Webb can detect with extraordinary sensitivity. The challenge of finding these molecular signatures is almost incomprehensible. Imagine trying to detect the light from a firefly hovering next to a blazing searchlight from 1,000 miles away. The star K2-18 is billions of times brighter than the planet orbiting it. Yet, Webb can pick out the faint infrared glow of molecules in the planet's atmosphere with pinpoint accuracy. Webb's secret weapon is its coronagraph technology. Originally designed to block starlight and reveal objects hiding in the glare, advanced image processing techniques subtract the overwhelming brightness of the star, leaving behind the faint infrared signatures of atmospheric molecules. It's like using a sophisticated filter to remove the roar of a jet engine so you can hear a whisper underneath. The detection of dimethyl sulfide on K2-18b required Webb to operate at the very limits of its capabilities. The molecule produces an infrared signature so faint that it took multiple observations over several months to confirm its presence. Each observation captured just a few photons of light that had traveled 120 light-years through the vacuum of space, carrying information about life on another world. But Webb's most remarkable achievement might be its ability to measure temperature with incredible precision. The telescope detected that K2-18b maintains a surface temperature of exactly 120 degrees Fahrenheit, warm enough to support liquid water, but cool enough to prevent complete evaporation. This temperature reading, accurate to within a few degrees across interstellar distances, represents one of the most precise measurements ever made of an exoplanet's environment. The data processing required to extract these discoveries from the raw infrared observations involves some of the most advanced computer algorithms ever developed. Artificial intelligence systems analyze millions of data points, searching for patterns so subtle that they would be invisible to human observers. The discovery of life on K2-18b represents not just a triumph of engineering, but a testament to humanity's ability to push the boundaries of what's possible. 120 degrees Fahrenheit. The number seems almost too perfect to be real. It's the temperature of a hot summer day in Death Valley, the warmth of a relaxing hot tub, the heat of a fevered human body fighting infection. On K2-18b, it's the temperature that makes life possible across an entire world. Temperature is everything when it comes to life. Too cold, and water freezes into ice that can't support the complex chemical reactions life requires. Too hot, and water boils away into steam, leaving behind a lifeless desert. The range where liquid water can exist, what scientists call the habitable zone, is surprisingly narrow. Earth sits almost exactly in the middle of this zone around our sun. A cosmic accident that allowed life to flourish for billions of years. But K2-18b's perfect temperature isn't an accident. It's the result of a delicate balance between stellar energy and atmospheric chemistry that creates conditions more stable than anything found on Earth. The planet orbits its red dwarf star at a distance where it receives almost exactly the same amount of energy per square meter as Earth receives from our sun. This cosmic coincidence means that despite being 120 light-years away, K2-18b exists in essentially the same thermal environment as our own world. The hydrogen atmosphere plays a crucial role in maintaining this perfect temperature, unlike Earth's thin nitrogen atmosphere, which allows heat to escape rapidly into space. K8b's thick hydrogen envelope acts like a planetary blanket. The hydrogen molecules trap infrared radiation, creating a greenhouse effect that keeps the planet warm, even on the night side, which never sees sunlight due to the planet's locked rotation. This stable temperature creates something unprecedented in our solar system, a world where liquid water can exist everywhere, from the perpetual day side to the eternal night side. On Earth, temperature variations between day and night, summer and winter, poles and equator create complex weather patterns and climate zones. On K2-18b, the thick atmosphere redistributes heat so efficiently that the entire planet maintains a consistent, life-friendly temperature. The implications for life are staggering. Earth's temperature variations create stress on living organisms, forcing them to adapt to seasonal changes, migrate to survive winter, or develop complex physiological mechanisms to regulate their internal temperature. On K2-18b, life would face no such challenges. The stable temperature would allow organisms to invest energy in growth, reproduction, and evolution rather than survival. But perhaps most remarkably, the 120-degree temperature on K2-18b falls within the range where life as we know it can not only survive, but thrive. Laboratory experiments have shown that biological processes can operate efficiently at temperatures up to 250 degrees Fahrenheit. At 120 degrees, chemical reactions proceed rapidly enough to support complex metabolism while remaining cool enough to prevent the breakdown of essential biological molecules. The discovery of K2-18b's perfect temperature represents more than just a scientific curiosity. It's proof that the universe can create conditions for life that are not just habitable, but potentially more hospitable than Earth itself. In a cosmos where most planets are either frozen wastelands or molten hellscapes, K2-18b stands as a beacon of hope, a world where life doesn't just survive, but flourishes in perfect comfort. Dimethyl sulfide. The name might sound like a chemical tongue twister, but these three words represent the most important discovery in human history. When the James Webb Space Telescope detected this molecule in the atmosphere of K2-18b, it found something that has never been produced by any known non-biological process. It found the signature of life itself. On Earth, dimethyl sulfide is produced exclusively by living organisms. Phytoplankton in our oceans create this molecule as a byproduct of their metabolism, releasing it into the atmosphere where it influences cloud formation and weather patterns. Marine bacteria, certain types of algae, and even some plants produce dimethyl sulfide as part of their normal biological processes. But no geological process, no chemical reaction, no non-living system has ever been observed creating this molecule. The detection of dimethyl sulfide on K2-18b is revolutionary because it represents what scientists call a biosignature, a molecule that can only be produced by life. Unlike oxygen, which can be created by non-biological processes, or methane, which can leak from geological formations, dimethyl sulfide has no known abiotic source. Its presence in K2-18b's atmosphere is as close to proof of life as we can get, without actually seeing the organisms that produce it. The molecule's chemical structure tells a story of biological complexity. Dimethyl sulfide consists of sulfur atoms bonded to carbon-containing methyl groups, a combination that requires specific enzymes to create. These enzymes evolved on Earth over billions of years, developing as part of the sulfur cycle that helps regulate our planet's atmospheric chemistry. The fact that similar molecules exist on K2-18b suggests that life there has also evolved sophisticated biochemical pathways. But the most shocking aspect of the discovery is the abundance of dimethyl sulfide in K2-18b's atmosphere. The concentrations detected by Webb are orders of magnitude higher than what would be expected from a planet just beginning to develop life. This suggests that the biological processes on K2-18b are not just present, they're thriving on a planetary scale. The implications are staggering. If life on K2-18b is producing dimethyl sulfide at levels detectable from 120 light-years away, the biosphere must be enormous. We're not talking about microscopic organisms struggling to survive in isolated pockets. We're talking about a planetary ecosystem so vast and productive that it's actively changing the chemistry of an entire world's atmosphere. The discovery also raises profound questions about the nature of life itself. If organisms on K2-18b are producing dimethyl sulfide, they must have evolved similar biochemical pathways to life on Earth. This suggests that the basic chemistry of life, the use of carbon, hydrogen, oxygen, nitrogen, and sulfur to build complex molecules, might be universal. Life might not just be common in the universe. It might follow predictable patterns wherever it emerges. The detection of dimethyl sulfide represents more than just a scientific breakthrough. It's the moment humanity discovered that we're not alone in the universe. Somewhere 120 light-years away, under alien skies and in hydrogen-rich air, life is breathing, growing, and fundamentally changing the chemistry of an entire world. In the world of science, certainty is a rare and precious commodity. Scientists speak in probabilities, statistical confidence levels, and margins of error. They hedge their bets, qualify their statements, and acknowledge uncertainty. But when the James Webb Space Telescope data on K2-18b was analyzed, the numbers told a story so clear that even the most conservative scientists couldn't ignore it. There was a 99.7% chance that the dimethyl sulfide signal was real. To understand what this means, imagine flipping a coin 1,000 times. The probability of getting heads or tails on any single flip is 50%. But the probability of getting heads 997 times out of 1,000 flips is so small that it would never happen by chance in the entire history of the universe. That's the level of statistical confidence scientists have in the detection of life on K2-18b. The confidence level comes from a sophisticated statistical analysis called sigma detection. In particle physics and astronomy, scientists use sigma levels to measure how likely it is that a signal represents a real discovery rather than random noise. A 3 sigma detection means there's a 99.7% chance the signal is real, and only a 3 in 1,000 chance it's a false alarm. This is the same statistical threshold used to discover new subatomic particles, confirm the existence of gravitational waves, and validate the most important discoveries in modern science. But reaching this level of confidence for an exoplanet atmosphere required unprecedented precision. The dimethyl sulfide signal is extraordinarily faint, just a few parts per billion in the infrared spectrum. To detect it, Webb had to measure wavelengths of light to an accuracy of 1 part in 10 million. Like measuring the width of a human hair to the precision of a single atom. The analysis involved multiple independent observations over several months, each one confirming the presence of the dimethyl sulfide signature. Different instruments on Webb detected the same molecular fingerprint at different wavelengths, providing redundant confirmation of the discovery. Computer algorithms analyzed millions of data points, searching for systematic errors or contamination that could explain the signal. None were found. The statistical analysis also considered alternative explanations for the signal. Could it be caused by unknown atmospheric chemistry? Could it be contamination from Earth? Could it be an artifact of the telescope's instruments? Each possibility was tested and ruled out with mathematical precision. The only explanation that fits the data is the biological production of dimethyl sulfide by living organisms on K2-18b. This level of certainty is almost unprecedented in exoplanet science. Most discoveries of atmospheric molecules on distant worlds are reported with much lower confidence levels, often barely reaching the threshold for publication in scientific journals. The 99.7% confidence in the K218b biosignature represents a quantum leap in our ability to detect life beyond Earth. The implications of this statistical certainty extend far beyond astronomy. When scientists say they're 99.7% certain that life exists on K218b, they're making a statement as reliable as any other fact in science. It's as certain as the existence of DNA, as solid as the theory of relativity, as established as the age of the universe. We are no longer wondering if life exists elsewhere. We know it does. Beneath the alien skies of K218b lies an ocean unlike anything in our solar system. It's not made of water alone, but of water mixed with hydrogen under pressures that would crush any Earth-based life form. Yet, this hydrogen ocean might be the most life-friendly environment in the known universe. The ocean exists because of K218b's unique atmospheric chemistry. The planet's hydrogen atmosphere doesn't just float above the surface. It dissolves into the liquid water, creating a solution that remains stable across a much wider range of temperatures and pressures than pure water. This hydrogen-water mixture can exist as a liquid from near freezing to over 300 degrees Fahrenheit, giving life an enormous range of conditions in which to thrive. On Earth, the deepest parts of our oceans are under crushing pressure, nearly 1,000 times greater than at the surface. Most life forms cannot survive at these depths, limited by the pressure that would collapse their cellular structures. But on K218b, the hydrogen in the water acts like a natural pressure buffer, allowing the liquid to maintain properties similar to water at much lower pressures, even at great depths. The hydrogen ocean also solves one of the biggest challenges for life on exoplanets' atmospheric loss. Earth's atmosphere is slowly bleeding away into space, and in a few billion years, our planet will become as airless as Mars. But K218b's hydrogen ocean acts like a massive atmospheric reservoir. As hydrogen is lost to space, more dissolves out of the ocean to replace it, potentially maintaining a stable atmosphere for trillions of years. The chemistry of this hydrogen ocean opens up possibilities for life that don't exist on Earth. Hydrogen can serve as an energy source for biological processes, allowing organisms to literally breathe the ocean itself. On Earth, some bacteria can metabolize hydrogen, but they're limited by its scarcity in our atmosphere. On K218b, hydrogen-breathing organisms could thrive in an environment where their primary energy source is essentially unlimited. But perhaps most remarkably, the hydrogen ocean could support life forms that are completely transparent to our conventional methods of detection. Traditional searches for life focus on oxygen-producing organisms like plants and algae. But on K218b, the primary life forms might be hydrogen-metabolizing organisms that produce entirely different chemical signatures. The dimethyl sulfide detected by Webb might be just one of many biosignatures in an alien ecosystem based on hydrogen chemistry. The ocean's depth remains a mystery. Computer models suggest it could be hundreds of miles deep, far deeper than any ocean on Earth. This vast volume of liquid water mixed with hydrogen could harbor ecosystems of unimaginable complexity and diversity. The stable temperature and pressure conditions could allow life to evolve in ways impossible on Earth, potentially reaching levels of complexity that we can barely imagine. The discovery of K218b's hydrogen ocean represents a fundamental shift in our understanding of habitable environments. We're no longer looking for worlds like Earth. We're looking for worlds that might be better than Earth. In the hydrogen oceans of super-Earths around red dwarf stars, life might not just survive, but flourish in ways that make Earth's biosphere seem limited by comparison. The atmospheric chemistry of K218b reads like science fiction, but it's real, and it's spectacular. while Earth's atmosphere is a simple mixture of nitrogen and oxygen. Ku-18b's atmosphere is a complex cocktail of molecules that create conditions both alien and surprisingly familiar. Methane swirls through hydrogen clouds. Carbon dioxide forms crystalline structures in the upper atmosphere, and under the right conditions, carbon atoms compress into diamond rain. The methane in Ku-18b's atmosphere tells a story of active biological processes. On Earth, methane is produced by everything from bacteria in swamps to cows digesting grass. It's one of the most common products of biological activity. Yet, it's also highly reactive, breaking down in the atmosphere within a few decades. The fact that Webb detected substantial amounts of methane on Ku-18b means something is actively producing it in vast quantities. But the methane on Ku-18b serves a purpose beyond just being a byproduct of life. In the hydrogen-rich atmosphere, methane acts as a crucial component in the carbon cycle, helping to regulate the planet's temperature and atmospheric chemistry. Organisms on Ku-18b might actually breathe methane, using it as an energy source in ways that would be impossible on Earth. The atmospheric pressure on Ku-18b creates conditions that would seem magical to Earth-based observers. At certain altitudes, the pressure and temperature are just right to compress carbon atoms into diamond crystals. These microscopic diamonds form in the upper atmosphere and rain down toward the surface, creating a constant shower of precious gems. But to the life forms on Ku-18b, these diamonds might be as common as raindrops are to us. The presence of carbon dioxide in the atmosphere adds another layer of complexity to the planet's chemistry. Unlike Earth, where carbon dioxide is a trace gas, Ku-18b's atmosphere contains substantial amounts of CO2 that interact with the hydrogen and methane in complex ways. This three-way chemical dance creates conditions that could support entirely different forms of photosynthesis than anything found on Earth. The atmospheric dynamics on Ku-18b are driven by the planet's locked rotation, where one side always faces the star while the other remains in perpetual darkness. This creates massive atmospheric currents that carry heat, moisture, and chemical compounds from the day side to the night side. The result is a planet-wide weather system that constantly mixes and redistributes the atmospheric chemistry, creating conditions that remain stable across the entire surface. The thick atmosphere also protects any surface life from harmful radiation. Red dwarf stars like K2-18 are known to produce powerful flares that could sterilize planet surfaces. But K2-18b's dense hydrogen atmosphere acts like a natural shield, absorbing and deflecting radiation that would be lethal to Earth-based life. This protection might be crucial for allowing complex life to evolve and thrive on the planet's surface. The chemical complexity of K2-18b's atmosphere suggests that life there might be far more sophisticated than anything on Earth. In an environment where diamonds rain from the sky and methane serves as breath, evolution might have taken paths that would seem impossible to us. The biosignatures detected by Webb might be just the beginning of a biochemical story that rewrites our understanding of what life can be. K2-18 is not a star like our Sun. It's a red dwarf, smaller, cooler, and dimmer than the star that lights our world. But this seemingly modest star might be the most important type of star in the universe when it comes to supporting life. While our Sun will eventually expand into a red giant and destroy all life on Earth, K2-18 will burn steadily for trillions of years, providing stable energy for eons that dwarf the entire current age of the universe. Red dwarf stars make up about 75% of all stars in the galaxy, making them the most common type of star in the cosmos. They're small, typically less than half the mass of our Sun, and they burn their nuclear fuel so slowly that they can maintain a steady energy output for periods longer than the current age of the universe. While our sun has a lifespan of about 10 billion years, red dwarfs can shine for up to 10 trillion years. This incredible longevity has profound implications for life. On Earth, complex life took nearly 4 billion years to evolve from simple bacteria to the diverse ecosystems we see today. If life on K2-18b has had even a fraction of the time available around its red dwarf star, it could have reached levels of complexity and sophistication that make Earth's biosphere seem primitive by comparison. The star K2-18 is relatively quiet compared to some red dwarfs, which are known for producing powerful stellar flares that could sterilize planet surfaces. These flares can increase a star's energy output by thousands of times for hours or days, bombarding nearby planets with lethal radiation. But K2-18 appears to be what astronomers call a well-behaved red dwarf, with minimal flare activity that allows its planets to maintain stable atmospheres and potentially support life. The stable energy output of K2-18 creates conditions that are remarkably similar to Earth's, despite the star being much smaller and cooler than our Sun. The planet K2-18b orbits much closer to its star than Earth orbits the Sun, completing one orbit in just 33 days. But because the star is cooler, this close orbit places the planet in the perfect position to receive almost exactly the same amount of energy per square meter as Earth receives from our Sun. This cosmic coincidence means that K2-18b exists in what astronomers call the Goldilocks zone, not too hot, not too cold, but just right for liquid water to exist on the surface. But unlike Earth, which will eventually be destroyed when our Sun expands into a red giant, K2-18b could remain in this perfect zone for trillions of years, providing an almost unlimited timescale for life to evolve and develop. The gravitational relationship between K2-18b and its star has also created tidal locking, where one side of the planet always faces the star while the other remains in perpetual darkness. This might seem like a disadvantage, but the planet's thick atmosphere redistributes heat so efficiently that both sides maintain comfortable temperatures. The result is a world with a permanent day side and a permanent night side, each offering different environments for life to explore and exploit. K2-18 represents more than just a star. It's a promise of cosmic stability that could nurture life beyond our wildest dreams. The distance to K2-18b is both impossibly vast and tantalizingly close. 120 light-years means that the light we're seeing from this world left its surface when Teddy Roosevelt was President of the United States. It's a distance so enormous that our fastest spacecraft would take over 2 million years to reach it. Yet, it's practically next door in cosmic terms. To put this distance in perspective, imagine shrinking the entire Milky Way galaxy to the size of North America. Earth would be smaller than a grain of sand, and K2-18b would be another grain of sand, about the width of a small town away. In a galaxy containing over 100 billion stars, K2-18b is close enough that we can study its atmosphere in detail, analyze its chemical composition, and detect the signatures of life itself. The light that carries information about K2-18b's atmosphere has traveled through the vacuum of space for 120 years, crossing the vast emptiness between stars while carrying the molecular fingerprints of an alien world. When that light finally reaches the mirrors of the James Webb Space Telescope, it's so faint that Webb must collect photons for hours just to detect the presence of a single molecule in the planet's atmosphere. But distance works in our favor as well as against us. The 120 light-year journey acts like a cosmic time machine, allowing us to observe K2-18b as it existed over a century ago. The dimethyl sulfide signatures we're detecting were produced by living organisms when Earth was just beginning to industrialize. We're literally seeing the breath of alien life from the past. The implications of detecting life at this distance are staggering. If we can identify biosignatures on K2-18b from 120 light-years away, it means the biological activity on that world must be enormous. The organisms producing dimethyl sulfide aren't just surviving, they're thriving on a planetary scale, creating atmospheric signatures so strong they can be detected across interstellar space. This distance also makes K2-18b a perfect target for future observations. While it's too far away for any conceivable human mission, it's close enough that we can study it in extraordinary detail with increasingly powerful telescopes. The upcoming extremely large telescope, with a mirror over 100 feet across, will be able to analyze K2-18b's atmosphere with unprecedented precision, potentially detecting dozens of different biosignatures. The 120 light-year distance places K2-18b within what astronomers call the local neighborhood of stars. This region contains several thousand star systems, many of which likely harbor planets. If life exists on K2-18b, it suggests that our local galactic neighborhood might be teeming with living worlds, each developing their own unique biospheres and evolutionary paths. Perhaps most remarkably, the distance to K2-18b means that if there's intelligent life on that world, they could be detecting signs of life on Earth right now. The radio signals we've been broadcasting into space for the past century are just now reaching their neighborhood, potentially announcing our presence to any civilization advanced enough to detect them. We're not just discovering life on a distant world, we're potentially making first contact across the vast darkness between stars. The challenge seemed impossible. How do you photograph a firefly hovering next to a searchlight from 1,000 miles away? That's essentially what the James Webb Space Telescope needed to do to capture direct images of planets like K2-18b. The star K2-18 is billions of times brighter than the planet orbiting it, creating a glare so intense that it would normally make detecting the planet completely impossible. The solution came from an unexpected source, studying our own sun. For decades, astronomers have used devices called coronagraphs to block out the sun's blinding light and observe its corona, the faint outer atmosphere that's normally invisible against the star's brilliant surface. Webb's engineers adapted this technology for exoplanet detection, creating what might be the most sophisticated light-blocking system ever devised. Webb's coronagraph works like a carefully engineered eclipse. A series of precisely shaped masks and mirrors block the star's light while allowing the much fainter light from orbiting planets to pass through. But this isn't just a simple disk blocking the star. It's a complex system of multiple masks, each designed to eliminate specific types of light contamination. The tolerances are so precise that a misalignment of just a few billionths of a meter would ruin the entire observation. The coronagraph's performance is measured in something called contrast ratio, how much fainter the planet is compared to its star. For K2-18b, this ratio is approximately 10 billion to 1. To put this in perspective, imagine trying to spot a single candle burning next to the brightest stadium lights during a night game while looking through a telescope from the opposite side of the country. The coronagraph makes this impossible task routine. But blocking the star's light is only half the battle. Once the starlight is removed, astronomers must deal with what they call speckles, tiny imperfections in the telescope's optics that create false signals mimicking planets. Advanced computer algorithms analyze these speckles in real time, using artificial intelligence to distinguish between genuine planetary signals and optical artifacts. The processing power required is staggering, equivalent to analyzing millions of photographs simultaneously to find one specific face in a crowd. The coronagraph's success depends on Webb's unprecedented stability. The telescope must maintain its position in space with an accuracy of milliseconds, equivalent to holding a laser pointer steady enough to hit a dime on the moon. Any vibration, any drift, any slight movement would blur the delicate observations and make planet detection impossible. Perhaps most remarkably, the coronagraph doesn't just block light, it actively shapes it, using a technique called wavefront correction. The system constantly adjusts the incoming light to create the perfect conditions for planet detection. It's like having a cosmic lens that can bend and focus light in ways that reveal hidden worlds orbiting distant stars. The coronagraph technology that revealed K2-18b represents just the beginning of a revolution in exoplanet detection. Future telescopes will use even more advanced coronagraphs capable of detecting Earth-sized planets around Sun-like stars, potentially revealing dozens of worlds where life might exist. But the coronagraph's greatest achievement isn't just technological, it's philosophical. By allowing us to see worlds that were previously invisible, it has opened a window into a cosmic neighborhood we never knew existed. When astronomers first calculated the mass of K2-18b, they discovered something that challenged everything they thought they knew about planetary habitability. The planet weighs in at 8.6 times the mass of Earth, making it roughly similar to Saturn in terms of total mass. Yet, unlike Saturn, which is a gas giant with no solid surface, K2-18b appears to be a water world with conditions that could support life more effectively than Earth itself. The relationship between planetary mass and habitability is complex and counterintuitive. On Earth, we're used to thinking of our planet's size as perfect for life, large enough to hold on to an atmosphere, small enough to maintain a comfortable surface gravity. But K2-18b proves that bigger can actually be better when it comes to supporting life over cosmic timescales. The planet's massive size creates a surface gravity nearly 3 times stronger than Earth's. While this might seem like a disadvantage, the intense gravity serves crucial functions that actually enhance habitability. The strong gravitational field holds onto the planet's atmosphere with an iron grip, preventing it from bleeding away into space, like Mars lost its atmosphere billions of years ago. Even the most violent stellar flares from the host star cannot strip away K2-18b's thick atmospheric envelope. This gravitational advantage extends to the planet's ability to retain water. On Earth, we lose water to space through a process called atmospheric escape, where water vapor in the upper atmosphere is broken apart by solar radiation, allowing hydrogen to drift away forever. K2-18b's powerful gravity prevents this loss, creating a world where water can accumulate over billions of years rather than gradually disappearing. The planet's mass also affects its internal structure in ways that benefit life. The intense pressure at K2-18b's core likely prevents the formation of the kind of solid iron core that Earth possesses. Instead, the planet may have a water ice core surrounded by layers of liquid water hundreds of miles deep. This creates a planetary ocean that dwarfs all of Earth's oceans combined, providing an enormous environment for life to develop and diversify. But perhaps most importantly, K2-18b's mass places it in a sweet spot that astronomers call the super-Earth category. These worlds are large enough to maintain thick atmospheres and deep oceans, but not so large that they become gas giants like Jupiter or Saturn. The boundary between rocky super-Earths and gaseous mini-Neptunes appears to be crucial for habitability, and K2-18b sits precisely in this optimal range. The planet's mass also influences its thermal evolution. Larger planets retain heat longer, potentially maintaining warm conditions for trillions of years, while Earth's interior is slowly cooling and will eventually become geologically dead. K18b's massive size means it could remain geologically active for periods longer than the current age of the universe. This long-term geological activity could drive the carbon cycle and atmospheric chemistry that maintain stable conditions for life. The discovery of K218b revolutionizes our understanding of planetary habitability. We're no longer looking for Earth's twin. We're looking for Earth's bigger, more stable, longer-lived cousin. The star system around CE Antliae is a cosmic nursery where worlds are still being born. At just 6.4 million years old, this red dwarf star is barely out of its stellar infancy, still surrounded by the disk of debris from which planets continue to form. But this youth comes with a price. The violent processes of stellar and planetary formation create conditions that would seem hostile to life, yet might actually be essential for creating the complex chemistry that life requires. Young stars like CE Antliae are notoriously unstable, prone to massive flares that can increase their energy output by thousands of times for hours or days. These stellar tantrums bombard nearby planets with radiation intense enough to strip away atmospheres and sterilize surfaces. Yet the planet discovered in this system, with its surface temperature of 120 degrees Fahrenheit, appears to have not only survived these violent outbursts, but potentially benefited from them. The debris disk surrounding CE Antliae is a scene of ongoing planetary formation. The disk is divided into 3 distinct rings, each containing different types of material at different stages of assembly. The innermost ring contains fine dust and rocky fragments that are gradually clumping together to form planetesimals. The middle ring, where the new planet orbits, contains larger chunks of rock and ice that are being swept up by the planet's gravity. The outer ring contains pristine material that hasn't yet been disturbed by planetary formation. This ongoing accretion process means that the planet is still growing, gathering material from the surrounding debris disk and potentially increasing its mass over time. The violent collisions between the planet and this debris create conditions of extreme heat and pressure that could drive the complex chemistry necessary for life. Each impact brings new materials and energy to the planet's surface, creating a dynamic environment where chemical evolution can proceed rapidly. The young star's high energy output also drives atmospheric chemistry in ways that might be crucial for life. The intense ultraviolet radiation breaks apart simple molecules in the planet's atmosphere, creating reactive fragments that can combine into more complex compounds. This stellar chemistry factory might be producing the organic molecules that serve as the building blocks for life, seeding the planet with the raw materials for biological evolution. But perhaps most remarkably, the planet appears to be gravitationally sculpting the debris disk, creating the gaps and structure that allowed astronomers to discover it. The planet's gravity shepherds material in the disk, clearing out its orbital path while simultaneously gathering material to fuel its continued growth. This dynamic interaction between planet and disk creates a feedback loop that could accelerate both planetary formation and the development of complex atmospheric chemistry. The discovery of a potentially habitable world in such a young system challenges our assumptions about when life can emerge. If life can develop in the chaotic environment of a forming planetary system, then the universe might be filled with worlds where biology and geology evolve together, creating conditions for life that are far more robust and adaptable than anything we see on Earth. The violence of stellar birth might not be an obstacle to life. It might be the crucible in which life learns to thrive in the most extreme conditions the universe can create. In the debris disk surrounding CE Antliae, there's a gap that defies explanation by conventional physics. The empty space between the first and second rings of debris should be filled with dust and rocky fragments. Yet it's almost completely clear of material. This gap, stretching across millions of miles of space, can only be explained by the presence of a hidden world that has swept up all the material in its orbital path. The gap represents a cosmic mystery that took years to solve. When astronomers first observed the CE Antliai system with ground-based telescopes, they could see the overall structure of the debris disk, but couldn't determine what was creating the empty spaces. The gaps were too large to be explained by magnetic fields or pressure waves and too clean to be the result of random collisions. Something massive had to be clearing out the material. But that something was invisible to conventional telescopes. The James Webb Space Telescope's infrared vision finally revealed the answer. Hidden in the gap was a faint infrared source, glowing with the heat of a young planet that had swept up all the debris in its orbital zone. The planet, now designated this world, has a mass similar to Saturn's but orbits much closer to its star, creating gravitational forces strong enough to clear out a gap millions of miles wide. The precision of this gap is what makes it so remarkable. Planetary formation theory predicts that growing planets should create gaps in debris disks. But the gap around this world is almost perfectly clean, suggesting that the planet has been in its current orbit for a significant period of time. This challenges our understanding of how quickly planets can form and begin affecting their environment. But the gap tells a deeper story about planetary formation. The clean edges of the gap suggest that the planet's gravity is not just clearing out material, but actively organizing it. The debris that would normally orbit chaotically is being shepherded into the ring structures that frame the gap, creating a complex gravitational dance that shapes the architecture of the entire system. Computer simulations of the CE Antliai system reveal that the planet's gravity creates resonant zones where debris can accumulate safely without being swept up by the planet. These zones correspond exactly to the locations of the observed rings, confirming that the planet is actively sculpting the structure of the debris disk. The planet isn't just orbiting passively. It's acting as a cosmic architect, designing the layout of its stellar system. The gap also provides clues about the planet's composition and history. The material that has been swept up by the planet includes water-rich comets and asteroids, suggesting that the world has acquired the volatile compounds necessary for developing atmospheres and potentially supporting life. The planet's current temperature of 120 degrees Fahrenheit indicates that it has retained enough of this material to maintain a substantial atmosphere. Perhaps most remarkably, the gap suggests that planetary formation is a more orderly process than previously thought. Instead of random collisions and chaotic accumulation, planets appear to create organized structures that persist for millions of years. The gap around this world represents not just an empty space, but a footprint of gravitational architecture that reveals how worlds shape their cosmic neighborhoods. 120 degrees Fahrenheit. This temperature appears again and again in the most promising discoveries of potentially habitable worlds, as if the universe has found the perfect setting for life to flourish. It's warm enough to drive rapid chemical reactions and maintain liquid water, yet cool enough to prevent the breakdown of complex organic molecules. On multiple worlds discovered by the James Webb Space Telescope, this temperature represents the sweet spot where life can not only survive, but thrive. The significance of this temperature extends far beyond simple habitability. At 120 degrees, water exhibits properties that are ideal for supporting life. The liquid is warm enough to dissolve a wide range of chemical compounds, creating solutions that can transport nutrients and waste products efficiently. The temperature accelerates biochemical reactions, allowing metabolic processes to proceed at rates that support active life while remaining slow enough to maintain stable molecular structures. But 120 degrees Fahrenheit also represents something more profound, the temperature at which Earth's most extreme life forms thrive. In deep-sea hydrothermal vents, where temperatures reach similar levels, life has evolved some of its most remarkable adaptations. These environments host organisms that use chemical energy instead of sunlight, creating ecosystems that are completely independent of surface conditions. The discovery of worlds with similar temperatures suggests that such chemosynthetic life might be common throughout the universe. The temperature also creates ideal conditions for the formation of complex organic molecules. Laboratory experiments have shown that temperatures around 120 degrees Fahrenheit are optimal for the synthesis of amino acids, the building blocks of proteins. This temperature range allows for the chemical reactions that create life's essential molecules while preventing the thermal breakdown that would destroy them at higher temperatures. On multiple worlds, this temperature is maintained by different mechanisms, each revealing a different pathway to habitability. Some planets achieve this temperature through atmospheric greenhouse effects, where thick atmospheres of hydrogen or carbon dioxide trap heat from their stars. Others maintain 120 degrees through internal heat sources, where radioactive decay or gravitational compression provides the energy to warm the surface. A few worlds use a combination of both, creating remarkably stable temperature conditions. The consistency of this temperature across different planetary systems suggests that it might represent a fundamental optimum for life. Just as stars have preferred masses and sizes that allow them to burn stably for billions of years, planets might have preferred temperatures that allow life to develop complexity and diversity. The temperature of 120 degrees might be the cosmic setting where biology works best. Perhaps most remarkably, this temperature creates conditions that are not just habitable, but actively beneficial for life. The warmth accelerates evolution by increasing mutation rates and metabolic activity, while the stability prevents the temperature extremes that could drive species to extinction. Life on these worlds might evolve faster and more diversely than life on Earth, creating biospheres of unprecedented complexity. The discovery of multiple worlds at this perfect temperature suggests that the universe might be fine-tuned for life in ways we're only beginning to understand. The temperature sweet spot isn't just a coincidence. It might be the signature of a universe where life is not just possible, but inevitable. Methane should not exist in the atmosphere of K2-18b. This simple molecule, composed of one carbon atom surrounded by 4 hydrogen atoms, is highly reactive and breaks down quickly when exposed to ultraviolet radiation. Yet, the James Webb Space Telescope has detected substantial amounts of methane in the planet's atmosphere, creating a mystery that can only be solved by the presence of life actively producing this gas on a planetary scale. On Earth, methane is produced by a variety of biological processes. Bacteria in swamps and wetlands produce methane as they decompose organic matter in oxygen-free environments. Microorganisms in the digestive systems of animals create methane as they break down food. Even some plants produce methane as part of their metabolic processes. But all of these sources share one common characteristic: they're biological. No known geological process on Earth produces significant amounts of methane. The methane on K2-18b tells a story of active biological processes that might be even more prolific than those on Earth. The concentrations detected by Webb are orders of magnitude higher than what would be expected from geological sources, suggesting that the planet's biosphere is producing methane at rates that dwarf anything seen on Earth. This isn't just life surviving on an alien world. It's life thriving and reshaping atmospheric chemistry on a global scale. But the methane mystery goes deeper than just its production. The molecule's presence in K2-18b's hydrogen-rich atmosphere creates possibilities for biochemistry that don't exist on Earth. Methane can serve as both a carbon source and an energy source for organisms, potentially supporting ecosystems that breathe methane and metabolize it for energy. In the planet's unique atmospheric chemistry, methane might be as important to life as oxygen is to Earth-based organisms. The interaction between methane and hydrogen in K2-18b's atmosphere could create complex organic molecules that serve as the building blocks for life. Laboratory experiments have shown that methane and hydrogen can combine under the right conditions to form amino acids, the components of proteins. The planet's atmospheric chemistry might be acting as a giant biochemical factory, producing the organic compounds that life needs to develop complexity. The methane also provides clues about the planet's evolutionary history. The molecule's presence suggests that K2-18b has maintained active biological processes for extended periods, possibly millions or billions of years. This indicates that the planet's climate and atmospheric chemistry have been stable enough to support life over geological timescales, creating conditions where evolution can proceed toward increasing complexity. Perhaps most remarkably, the methane on K2-18b might be just one component of a much larger atmospheric ecosystem. The planet's atmosphere contains a complex mixture of gases that interact with each other in ways that could support multiple types of metabolism. Different organisms might use different atmospheric components as energy sources, creating a layered ecosystem that spans the entire atmosphere from surface to space. The methane mystery represents more than just a chemical puzzle. It's evidence of a living world where biology and atmospheric chemistry have co-evolved to create conditions that support life on a scale beyond anything in Earth's history. The planet's atmosphere isn't just a mixture of gases. It's a living system that breathes with the rhythm of an entire biosphere. The discoveries made by the James Webb Space Telescope on K2-18b and other potentially habitable worlds represent just the beginning of a revolutionary observation campaign that will reshape our understanding of life in the universe. Armed with the knowledge that biosignatures can be detected across interstellar distances, astronomers are preparing an unprecedented survey of nearby star systems that could reveal dozens of living worlds within the next decade. The next phase of observations will focus on what astronomers call the Biosignature Survey, a systematic search for the chemical signatures of life in the atmospheres of planets orbiting nearby stars. This campaign will target over 200 star systems within 100 light-years of Earth, analyzing the atmospheric composition of every potentially habitable world that can be observed. The goal is nothing less than creating the first comprehensive catalog of life in our cosmic neighborhood. Webb's upcoming observations will use increasingly sophisticated techniques to detect fainter biosignatures and smaller planets. New observing modes will allow the telescope to study planets that don't transit their stars from Earth's perspective, vastly expanding the number of worlds that can be analyzed. Advanced computer algorithms will search for complex combinations of molecules that could indicate not just life, but different types of life based on alternative biochemistries. The observation campaign will also focus on time series analysis, studying how atmospheric compositions change over months and years. On Earth, our atmosphere shows seasonal variations as life responds to changing conditions. Similar variations on exoplanets could reveal not just the presence of life, but active biological cycles that respond to planetary seasons, stellar activity, or other environmental changes. One of the most exciting aspects of the next observation campaign is the search for what astronomers call technosignatures, the chemical evidence of technological civilization. Industrial processes produce distinctive atmospheric pollutants that could be detected across interstellar distances. The observation of artificial gases in an exoplanet's atmosphere would provide the first direct evidence of technological intelligence elsewhere in the universe. The campaign will also coordinate with other observatories around the world and in space. Radio telescopes will search for artificial signals from star systems where Webb detects biosignatures. Optical telescopes will look for signs of artificial lighting on the night sides of potentially inhabited worlds. This multi-wavelength approach will provide the most comprehensive search for life and intelligence ever attempted. Future observations will benefit from technological advances that are already in development. Improved coronagraphs will allow Webb to study smaller, more Earth-like planets. New spectrographs will provide higher resolution analysis of atmospheric chemistry. Advanced image processing techniques will extract more information from the same observations, potentially revealing biosignatures that are currently below the detection threshold. The observation campaign represents more than just a scientific program. It's humanity's first systematic attempt to map the distribution of life in the galaxy. Within the next decade, we may have identified hundreds of living worlds, each with its own unique biosignature and evolutionary history. The universe may reveal itself to be not just habitable, but abundantly alive. The next observation campaign will answer the greatest question in science: are we alone? The answer appears to be a resounding no, and we're about to discover just how much company we have in the cosmos. The debris disk surrounding CE Antliae resembles a cosmic three-ring circus, with each ring containing different types of material at different stages of planetary formation. This organized structure reveals that planetary formation is not a chaotic process, but follows predictable patterns that create order from cosmic chaos. The three rings around CE Antliae represent different chapters in the story of how worlds are born. The innermost ring, closest to the star, contains the finest dust and smallest rocky fragments. This material is heated by the star's energy to temperatures that would melt lead. Yet it maintains a stable orbit in a narrow band just a few million miles from the stellar surface. The particles in this ring are constantly colliding and sticking together, gradually building up larger and larger aggregates that will eventually become the cores of rocky planets. The middle ring, where the newly discovered planet orbits, contains a mixture of rock and ice that tells the story of a world in the process of formation. This is where conditions are just right for both rocky and icy materials to exist, creating the complex chemistry that could lead to habitable worlds. The planet discovered in this ring has cleared out most of the original material, but the remaining debris shows evidence of ongoing accretion and growth. The outer ring contains the most pristine material in the system, composed largely of water ice and organic compounds that have remained frozen since the star's formation. This ring serves as a reservoir of volatile materials that could be delivered to inner planets by gravitational perturbations or collisions. The outer ring represents the deep freeze of planetary formation, where the building blocks of life remain preserved in cosmic cold storage. The spacing between the rings is not random, but follows mathematical relationships that reveal the gravitational architecture of the system. Each ring occupies a zone where orbital mechanics create stable conditions for material accumulation. The gaps between rings represent areas where gravitational resonances would disrupt orbits, preventing material from accumulating and creating the clean boundaries that separate the rings. The three-ring structure also reveals the timeline of planetary formation. The innermost ring shows the earliest stages, where dust grains are just beginning to stick together. The middle ring represents the intermediate stage, where planet-sized objects are clearing out their orbital zones. The outer ring shows the preservation of original material, waiting for the right conditions to begin its own journey toward planetary formation. Computer simulations of the CE Antliae system reveal that the three-ring structure is not static, but is evolving over time. Material slowly spirals inward from the outer rings, feeding the growth of planets in the inner system. The newly discovered planet acts as a gravitational barrier, preventing material from the outer rings from reaching the inner ring too quickly, creating a controlled feeding process that allows planets to grow steadily over millions of years. The three-ring circus around CE Antliae represents more than just a pretty cosmic structure. It's a window into the universal process of planetary formation. Similar ring structures have been observed around other young stars, suggesting that the organized chaos of planetary birth follows similar patterns throughout the galaxy. We're not just observing one stellar system, we're watching the universe manufacture new worlds. The planet discovered by the James Webb Space Telescope in the CE Antliae system has broken a fundamental record in exoplanet science. With a mass just 1/3 that of Jupiter, this world is the lightest planet ever directly imaged around another star. This achievement represents more than just a technological milestone. It demonstrates that Webb can detect and analyze worlds that are remarkably similar to planets in our own solar system. Previous direct imaging of exoplanets was limited to massive worlds, typically several times the mass of Jupiter. These super-Jupiters were easier to detect because their large size and high temperatures made them bright enough to be seen despite the overwhelming glare of their host stars. But the newly discovered world around CE Antliae is 10 times less massive than any previously imaged planet, pushing the boundaries of what's possible with current technology. The planet's low mass creates unique challenges for detection. Less massive planets are cooler and dimmer, making them much harder to distinguish from the bright background of their parent star. The light from this world is nearly 10 billion times fainter than the light from CE Antliae, requiring Webb to operate at the absolute limits of its sensitivity. The fact that the telescope can detect such a faint object represents a triumph of engineering and data analysis. But the planet's low mass also makes it scientifically fascinating. Objects with masses similar to Jupiter's represent a boundary in planetary formation between gas giants and smaller, rocky worlds. This planet sits right at that boundary, providing crucial insights into how planetary systems transition from massive gas giants to smaller, terrestrial worlds. Understanding this transition is key to predicting where habitable planets might form. The planet's mass also affects its potential for habitability. While Jupiter-mass planets are typically gas giants with no solid surface, this lighter world might have a solid core surrounded by a relatively thin atmosphere. The surface temperature of approximately 120 degrees Fahrenheit suggests that the planet retains enough atmospheric mass to maintain a greenhouse effect, but not so much that it becomes a runaway gas giant. The detection of this low-mass world required innovative observational techniques. Webb's infrared instruments had to distinguish between the planet's faint thermal emission and the much brighter scattered light from dust in the debris disk. Advanced image processing algorithms remove the contaminating light from the star and disk, revealing the planet's faint infrared glow. The entire process is like extracting a whisper from a thunderstorm. The planet's low mass also makes it an ideal target for future atmospheric studies. More massive planets have thick atmospheres that can hide their deeper atmospheric layers from observation. But this world's thinner atmosphere allows Webb to probe deeper into its composition, potentially revealing details about atmospheric chemistry that would be impossible to detect on more massive worlds. Perhaps most importantly, the detection of this low-mass world proves that Webb can find and study planets that are genuinely similar to those in our own solar system. This opens up the possibility of discovering and analyzing truly Earth-like worlds, bringing us closer to finding planets that might not just be habitable, but actually inhabited. The discoveries made by the James Webb Space Telescope represent just the beginning of a golden age in the search for extraterrestrial life. Planned observatories and technological advances over the next 2 decades will revolutionize our ability to detect and study life on distant worlds, potentially revealing a universe teeming with biological activity that spans the entire galaxy. The most ambitious of these future projects is the Habitable Worlds Observatory, a space telescope designed specifically to detect and analyze Earth-like planets around Sun-like stars. This observatory will use advanced coronagraph technology to achieve contrast ratios of 10 billion to 1, allowing it to directly image planets that are truly similar to Earth. The telescope will be capable of detecting the atmospheric signatures of oxygen, water vapor, and other biosignatures that could indicate the presence of life. Ground-based observatories are also pushing the boundaries of what's possible. The extremely large telescope, currently under construction in Chile, will have a mirror over 100 feet across, nearly 5 times larger than Webb's primary mirror. This massive telescope will be able to analyze the atmospheres of nearby exoplanets with unprecedented detail, potentially detecting dozens of different molecular species that could indicate biological activity. But the future of life detection extends beyond simply building bigger telescopes. Artificial intelligence and machine learning algorithms are being developed to analyze the vast amounts of data that these observatories will generate. These systems will be able to recognize patterns in atmospheric chemistry that might be too subtle for human observers to detect, potentially identifying forms of life based on completely different biochemistries than what we see on Earth. The next generation of life detection will also focus on what scientists call agnostic biosignatures, chemical signals that could indicate life without requiring assumptions about how that life operates. Instead of looking for specific molecules like oxygen or methane, these techniques will search for patterns of chemical disequilibrium that could only be maintained by active biological processes, regardless of the specific biochemistry involved. Perhaps most exciting is the development of technologies that could detect life in real time. Future observatories will be able to monitor changes in planetary atmospheres over periods of hours and days, potentially observing the daily breathing of entire biospheres. These observations could reveal not just the presence of life, but active biological cycles that respond to planetary rotation, seasonal changes, or other environmental factors. The future also holds the possibility of detecting technological civilizations directly. Advanced observatories will be sensitive enough to detect the atmospheric signatures of industrial processes, artificial lighting on the night sides of planets, and other signs of technological activity. The search for extraterrestrial intelligence will become a routine part of exoplanet characterization, potentially revealing not just life, but civilization throughout the galaxy. Within the next 20 years, we may have identified hundreds of living worlds, each with its own unique atmospheric chemistry and evolutionary history. The universe may reveal itself to be not just habitable, but abundantly alive, with biological processes operating on scales that dwarf anything in Earth's history. The future of life detection promises to answer humanity's greatest question: are we alone? The answer appears to be a resounding no, and we're about to discover just how much company we have. The moment will come without fanfare. A scientist in a laboratory will look at a computer screen showing data from the James Webb Space Telescope and realize that humanity's cosmic loneliness has ended forever. The evidence will be undeniable, a combination of atmospheric signatures that can only be explained by the presence of life actively transforming the chemistry of an entire world. In that instant, everything will change. The discovery of life on K2-18b has already brought us to the threshold of this moment. With 99.7% statistical confidence, we have detected the chemical signatures of biological activity 120 light-years away. the dimethyl sulfide in the planet's atmosphere, the complex interactions between methane and hydrogen, the chemical disequilibrium that can only be maintained by active biological processes all point to a world where life is not just present, but thriving on a planetary scale. But the moment of absolute certainty will come when multiple independent observations confirm what we already strongly suspect. Different telescopes will detect the same biosignatures. Alternative explanations will be systematically ruled out. The statistical confidence will rise from 99.7% to 99.99%. Then to certainty beyond any reasonable doubt. When that moment arrives, the implications will ripple through every aspect of human civilization. Science will be revolutionized as we grapple with the reality that biology is not unique to Earth, but a fundamental feature of the universe. Philosophy and religion will be transformed as we reconsider humanity's place in a cosmos that contains other forms of life. Technology will advance rapidly as we develop new methods to study and potentially communicate with life on distant worlds. The psychological impact on humanity will be profound. The knowledge that we are not alone will end the cosmic loneliness that has haunted our species since we first looked up at the stars and wondered if anyone was looking back. We will become members of a galactic community of living worlds, each following its own evolutionary path, but sharing the fundamental experience of life in the universe. But the moment will also bring new responsibilities. As we identify more living worlds, we will face ethical questions about our obligations to protect and preserve life throughout the galaxy. The discovery of extraterrestrial life will force us to develop new frameworks for understanding our relationship with the cosmos and our responsibilities as a spacefaring species. The moment we're no longer alone will mark the beginning of a new chapter in human history. We will transition from a species that wonders about life elsewhere to a civilization that knows life exists throughout the galaxy. The universe will be transformed from a vast, empty space into a cosmic ecosystem, teeming with biological activity and evolutionary experimentation. Looking back from that moment, we will recognize that the James Webb Space Telescope's discovery of biosignatures on K2-18b was the first step in humanity's journey from cosmic isolation to galactic citizenship. The chemical signatures detected in the atmosphere of a world 120 light-years away will be remembered as the evidence that ended our loneliness and began our understanding of our place in a living universe. We stand at the threshold of the greatest discovery in human history. The James Webb Space Telescope has peered across 120 light-years of space and found something that will change everything we thought we knew about our place in the universe. In the atmosphere of K2-18b, wrapped in hydrogen clouds and warmed to exactly 120 degrees Fahrenheit, life is breathing. The evidence is overwhelming. Dimethyl sulfide, a molecule produced only by living organisms, exists in concentrations that can be detected across interstellar space. The statistical confidence is 99.7%, as certain as any fact in science. The atmospheric chemistry tells a story of biological processes operating on a planetary scale, transforming the air of an entire world through the collective breath of countless organisms. But K2-18b is not alone. Webb has revealed a universe where potentially habitable worlds exist in abundance, each offering unique conditions for life to emerge and thrive. From the debris disks around young stars, where planets are still forming, to the ancient red dwarfs that will burn for trillions of years, the galaxy appears to be filled with environments where life can not only survive, but flourish. The implications extend far beyond astronomy. We are witnessing the end of humanity's cosmic loneliness and the beginning of our recognition as citizens of a galactic community. The universe is not empty space punctuated by rare pockets of life. It is a vast ecosystem where biological processes operate on scales that dwarf anything in Earth's history. The technologies that made these discoveries possible represent just the beginning. Future observatories will reveal the atmospheric signatures of hundreds of living worlds, each with its own unique biochemistry and evolutionary history. We may discover forms of life based on completely different chemistry than what we see on Earth, expanding our understanding of what life can be and how it can emerge. The moment we definitively confirm that we are not alone will mark a turning point in human civilization. Every child born after that moment will grow up knowing that life exists throughout the galaxy, that we are part of a cosmic community that spans the stars. The philosophical and spiritual implications will reverberate through every aspect of human culture. But perhaps most importantly, these discoveries remind us that life is not just possible in the universe. It appears to be inevitable. Wherever conditions allow, life emerges and transforms worlds. The chemical signatures detected by Webb are not just evidence of life on distant planets. They are proof that the universe itself is fundamentally alive. The James Webb Space Telescope has given us the first glimpse of our true cosmic neighborhood, revealing that we live in a galaxy where life is not the exception, but the rule. We are no longer alone, and we never were. The universe has been waiting for us to develop the technology to see what was always there. A cosmos teeming with life, breathing with the rhythm of countless biospheres, alive with possibilities we are only beginning to imagine.
The darkness was not absence. It was the pause before a breath, the moment before a thought becomes language. There were no stars, no time, no rhythm, only the absolute stillness of a silence that did not yet know it was silent. In that silence, something stirred. Not a spark, not even motion, just the possibility of becoming. And then, it began. Not with an explosion or a flash, but with the unraveling of non-existence into form. Space did not stretch into something that had once been empty. It was space itself that unfolded like a newborn wing, carrying with it time, temperature, and the tension of expansion. The first breath of being. In that instant, the universe bloomed not into stars, not yet, but into raw energy so dense it could not distinguish itself from itself. It surged outward faster than any particle could chase, a rush not of movement through space, but of space itself expanding. This was not like a fireball rising in the sky, but like an idea filling a mind that had only just been invented. Everything we know, atoms, stars, the breath you just took was still locked in potential. For the first 10 millionth of a trillionth of a second, there were no particles, only a sea of radiant tension, a field of quantum flickers where nothing held shape. Time ticked in intervals so small that the word interval loses meaning. But cooling brings structure, and as the young cosmos released its initial fever, it allowed the formation of the first fragments of form. Quarks jittered into existence, so restless they refused to be alone. Gluons danced between them, insisting on bonds that gave birth to protons and neutrons. This dance was violent and brief, and only in the narrowest window of temperature and timing could these particles hold hands long enough to matter. The air, though, there was no air thickened with interactions. From pure energy, from light itself, mass had begun to coalesce. These were not yet atoms. Electrons still soared too fast to be tethered, and light could not travel freely. The newborn universe was a clouded womb of charged particles, scattering photons like marbles across glass. If you had eyes in that fog, you would have seen nothing. If you had ears, you would have heard silence broken by the hiss of chaos. And yet something was beginning to change. Within those first few minutes, the universe cooled just enough for protons and neutrons to fuse. They created the simplest nuclei, hydrogen first, then helium, and the rare hint of lithium. This period, brief and irrevocable, stitched together the elemental thread from which all later complexity would be spun. The numbers, strange as they seem, still echo through the cosmos: 75% hydrogen, 25% helium, and traces so faint they barely whisper. These ratios were set not in stars, but in that primordial moment, when there were still no stars to shape or shine. The light that tried to escape could not. Electrons and photons collided endlessly, bouncing through a universe still too hot for stillness. But behind the fog, the orchestra was tuning. With every passing heartbeat of cosmic time, the temperature dropped, and the first outlines of permanence began to trace themselves into being. Soon, the forces that govern everything would begin to separate, each peeling away from the original unity that had once bound them. Gravity, the weak and strong nuclear forces. Electromagnetism, once indistinguishable, would take on distinct roles. Their divergence was not a collapse, but a kind of crystallization, like water freezing into geometric symmetry, defining shape and direction where none had existed before. And so, from a nothing that was not truly nothing, a universe took its first steps into becoming, not with thunder or light, but with quiet laws unfolding in a darkness too dense to allow vision, a darkness not of absence, but of infinite potential yet unshaped. 1,000,000 years might pass without a single sound if there is nothing to carry it. After the first 380,000 years, silence in the early universe was no longer just a metaphor. It was a physical reality. As the newborn cosmos exhaled its heat into ever-expanding space, its temperature fell below a threshold that allowed electrons, for the first time, to slow and settle into orbit around the nuclei that had formed long before them. The particles that had wandered like restless ghosts finally found their place, and from this delicate embrace, the first atoms emerged. That union did not merely create matter, it changed the very transparency of the universe. Light, once trapped in an endless ricochet of collisions, was suddenly released, and with it came a new kind of clarity. Photons poured into the openness, stretching and fading as space expanded, leaving behind a faint glow, a whisper of the infant cosmos that still surrounds us in all directions. This is the cosmic microwave background, the earliest light we can detect, not because it was the first, but because it was the first allowed to travel freely. Yet even with the birth of atoms and the liberation of light, the universe had no stars. The sky was dark, though not empty. It was filled with potential, with hydrogen and helium clouds drifting through space like scattered ash, remnants of a fire whose embers had not yet reignited. This was the age of silence in a different form, the time cosmologists call the Dark Ages, not because there was no activity, but because the light had not yet returned in new forms. Invisible threads of gravity began to tug gently at the vast sheets of gas. In some regions, matter clumped just slightly more densely than in others, and these tiny differences grew steadily over hundreds of millions of years. The universe was laying down a kind of scaffolding, invisible and immense, an intricate web upon which future galaxies would hang like dewdrops. There were no galaxies yet, no suns, no planets or moons, just darkness, and the slow tightening of gravity's fingers. Eventually, in these dense knots, clouds began to contract. As they collapsed under their own weight, the temperature at their centers began to rise. Pressure mounted, and then, quietly and invisibly, fusion was born. The first stars lit up like flares in the abyss. They were nothing like the stars we know, massive, short-lived, and unpolluted by the complex chemistry that defines our solar system. These were elemental furnaces, raw and primitive, composed almost entirely of hydrogen and helium. They lived fast and died violently, burning through their fuel in only a few million years. Their lives were short, but their deaths rewrote the cosmos. In their cores, under unimaginable heat, they had forged new elements, carbon, nitrogen, oxygen, pieces of a puzzle that had never before existed. When they exploded as supernovae, they hurled these creations into space, seeding the vast darkness with materials that would one day form planets, oceans, blood, and thought. The violence of these first explosions did not end in destruction. Their shockwaves compressed nearby gas clouds, triggering the birth of new stars, each formed from matter more complex than the last. A lineage had begun, a cosmic ancestry of stars, each generation inheriting a richer chemical legacy than the one before. But that was still in the future. In the universe's early years, Every new light that flared to life pushed back the darkness just a little more. As ultraviolet radiation from these ancient stars poured into space, it began to tear apart the hydrogen atoms that filled the void. Photons stripped electrons from protons, reionizing the universe, and in doing so, ending the cosmic dark ages. The universe, once dim and unformed, now shimmered with a growing lattice of starlight. Galaxies began to coalesce at the nodes of the cosmic web, spinning into spiral arms and elliptical clouds, dancing to the rhythm of gravity. What had begun as chaos had turned toward order, not because it was designed, but because the rules were written in the fabric of space and time. Still, nothing about this unfolding was predictable in the way we often imagine inevitability. If quantum fluctuations had danced just slightly differently, the stars we know, the planets we stand on, might never have formed. Our entire cosmic structure balances on the edge of these ancient uncertainties, ripples in the vacuum that inflation magnified into the framework of everything. A strange irony persists: the cold silence after the Big Bang had to last for hundreds of millions of years before heat and light could return in meaningful form. Before the sun could rise, the universe had to rest. Before atoms could bind into molecules, the space between them had to cool. In this long pause, the stage was set, not by force, but by the absence of it. And then, one star became many. One cloud gave rise to a cluster. One explosion echoed into dozens. And from this silent beginning, the sky learned to sing. The quiet chorus of stars, once scattered and few, began to crescendo into constellations of complexity. Galaxies, spun into being by the invisible architecture of dark matter, turned slowly in space, their spiraling arms cradling billions of suns. These spirals were not perfect or pristine. They grew through violence. Gravity, indifferent to the scale of suffering, pulled smaller galaxies into the bellies of larger ones. The sky itself became a history of collisions. Each encounter was both destruction and genesis. When galaxies merged, stars were flung into elliptical halos, gas clouds compressed into newborn clusters, and supermassive black holes at their centers edged closer, eventually coalescing in silence too deep for sound. These central black holes, once just strange theoretical outcomes of general relativity, became cosmic engines. As matter spiraled toward their event horizons, it heated and screamed in high-energy light, illuminating the cores of galaxies and powering quasars that shone more brightly than entire clusters. But even their brilliance could not overcome the strange truth that most of what exists does not shine. As telescopes reached further into the cosmic past, as instruments strained to measure gravitational pull versus visible mass, astronomers began to suspect an absence so massive it reshaped their understanding of presence. Stars spun in galactic disks faster than gravity from visible matter should allow. Something unseen was holding them together. Dark matter. Not because it is black or even shadowed, but because it neither absorbs nor emits light. It is invisible to every wavelength we know, detectable only by its gravity. It may outnumber normal matter by a factor of 5. It surrounds galaxies like a cloak and forms the very scaffolding upon which all visible structure is hung. It does not collide, does not clump into planets or stars, does not burn. And yet it is what allows the night sky to exist at all. Then there is the deeper silence, still dark energy. Unlike dark matter, which pulls, dark energy pushes. It is not a force we can localize or isolate. It permeates space itself, a kind of pressure written into the void. In the late 20th century, astronomers measuring the light of distant supernovae discovered something that stunned the field. The expansion of the universe was not slowing as expected, but accelerating. This defied centuries of assumptions. Gravity, even on cosmic scales, was expected to act as a brake, gradually slowing the outward rush born from the Big Bang. Instead, the galaxies are speeding away from one another faster with time, carried by a space that seems to stretch more eagerly the more it expands. No one fully knows what dark energy is. Some think it is the cosmological constant, a fudge factor Einstein once inserted into his equations and later called his greatest mistake. Others imagine it as a quantum field, fluctuating with the fabric of space-time. And still others wonder whether it is a sign that our understanding of gravity is incomplete at the grandest scales. Whatever its nature, its implications are clear. The fate of the universe may not be a gentle coasting or a collapsing return. It may be an eternal, accelerating separation. In time, galaxies beyond our local group will speed so far and so fast that their light will never reach us again. The night sky, once full of stars, will become a smaller and smaller window into a shrinking past. Even light itself is not eternal. Photons from the cosmic microwave background continue to stretch, their energy fading with every heartbeat of expansion. One day, even that background glow may fall below detection, and the record of the universe's birth will vanish from view. This accelerating drift is not a tearing or breaking. It is the absence of grip, the emptiness of distance growing too fast to be bridged. And though the galaxies still dance, though stars still burn and die, there is a slow inevitability building in the background, the quiet extinguishing of connection. We live in a golden age not because our time is special in its content, but because we can see. We are early enough that the echoes of the beginning still wash over us. We can study the birth of time, map the expansion of space, and trace the fingerprints of invisible forces. But this window will not stay open. The past is not only behind us, it is also fading. And so the stars remain, for now, as reminders of a universe that once burst from nothing into brilliance, that once seeded its silence with the raw ingredients of life. Their light crosses unimaginable distances to find us. But in the far future, the silence will grow again, not from absence, but from distance untraversed, light undelivered, and stories untold. A planet coalesced from dust and ash in the outer spirals of a medium-sized galaxy. Third from a yellow star, it spun without language for billions of years, collecting the minerals and elements flung outward by generations of dead stars. Carbon, forged in ancient cores. Iron, birthed in supernovae. Oxygen and nitrogen, drifting freely in interstellar clouds before gravity sculpted them into air and ocean. There was nothing inevitable about the shape it took. Seas did not have to form. Atmosphere did not have to hold. Life did not have to arise. But chemical restlessness danced across clay and hydrothermal vent. And eventually, patterns emerged that could make copies of themselves. Simple at first, then layered, folded, armored, motile. Complexity rose, not in a straight climb, but in fits of catastrophe and reinvention. Through extinction and mutation, intelligence emerged, not as a trait, but as an accident of survival. On this single planet, in this modest corner of the cosmos, matter began to wonder about itself. Eyes turned upward not just in fear or navigation, but in curiosity. Something in the minds shaped by starlight began to ask what stars were. That question took millennia to articulate, and longer still to answer. Eventually, tools of glass and steel were pointed at the sky. Telescopes extended the eye. Accelerators cracked apart the smallest pieces of the known. Mathematics began to uncover rhythms hidden beneath the visible. And slowly, the universe started to explain itself through the minds it had unwittingly produced. But in that very effort, noble, wondrous, there came a growing awareness of limits. The more we learned, the more fragile the known became. The constants of nature were not merely numbers. They were balances on a razor's edge, the strength of gravity, the charge of the electron, the density of dark energy, each tuned within narrow margins that permit galaxies, stars, chemistry, breath. If gravity were slightly stronger, stars would burn out in moments, collapsing into black holes before life could find a foothold. If it were slightly weaker, matter might never have clumped, leaving a universe of eternal fog. The ratio of forces, the timing of phase transitions, the presence of matter at all, none of it demanded by logic. All of it balanced so precariously that some began to wonder whether such precision could be coincidence. From that doubt arose the anthropic principle, not as theology, but as contemplation. Perhaps the universe appears tuned for life, because only a tuned universe allows observers to arise at all. There could be many universes, infinite or near so, each with different laws. Ours would then be unremarkable, just one bubble in a sea of failure and silence, where finally, the music played long enough to listen to itself. This idea leads to the multiverse, not a fantasy, but a theoretical consequence of inflation, quantum mechanics, or string theory, depending on the path taken. In some versions, new universes bud off from quantum fluctuations like dew on a spider's web, each isolated and unreachable. In others, our own universe exists on a brain floating in a higher dimensional space, colliding now and then with others like it, triggering new cosmic births. None of these are proven, but all are consistent with the mathematics that describe the world we can test. The more we try to locate our position in the cosmic order, the more the ground shifts beneath us. We may not be the center. We may not be unique. We may not even be necessary. And yet, the very act of imagining these possibilities is a kind of defiance. It is not comfort we seek, but clarity. If the universe is a rare bloom in a field of lifeless variables, then to know it even briefly is to hold something sacred, even if that word belongs more to poetry than physics. There is a kind of quiet reverence in realizing that we live not under a dome of stars, but inside a storm of probabilities that, for a while, permitted reflection. The night sky is not a ceiling, but a question, and we are the echo of that question trying to answer itself. Somewhere, deep in the cosmic distance, a galaxy is vanishing, not because it is collapsing or consumed, but because the space between it and us is expanding faster than its light can travel. It continues to exist, burns with stars, carries the momentum of 1 billion years of history, but its story is now forever beyond our reach. The night sky, so vast and generous in our time, is slowly losing its memory. In the far future, this quiet disappearance will become the norm. Galaxies will drift beyond the cosmic horizon, leaving behind only the local group, those few dozen that remain gravitationally bound to us. Beyond that, silence will thicken. The cosmos will not end in a crash or a fire, but in a soft dimming, like the last embers of a great fire cooling into blackness. The stars will age. Red dwarfs, the most enduring, will flicker for trillions of years, but even they will one day exhaust their fuel. White dwarfs will cool into black cinders. Neutron stars will spin their last. Black holes, the most patient objects in existence, will slowly evaporate through Hawking radiation, particle by particle, until even their mass becomes memory. What remains will not be empty in the way we think of it. It will be thin, cold, and vast. A universe where energy is so diffuse that no new complexity can arise. A place where every possibility has already played out, and no reset is coming. This scenario, known as the heat death, is not merely a theoretical curiosity. It is a natural consequence of entropy, the tendency of energy to spread, of structure to dissolve, of time to move only forward. And yet, it is not entirely bleak. For in this long, slow twilight, meaning is not dictated by duration. It is forged in the moments where perception exists. In the rare span when stars burn and minds awaken, when questions are asked and answers sought not to dominate, but to understand. We are of this universe, not merely in it. Our atoms were fused in stars. Our thoughts are electrochemical echoes of ancient energy, rearranged by biology into something that can doubt and wonder. Even if our kind disappears, even if the species vanishes long before the last light fades, that we existed at all reshapes the universe's story. Perhaps this, too, is a kind of cosmological inheritance, that from the laws that shaped stars and galaxies, something arose that could look back at those laws in awe, not because we were intended, but because we became capable of interpretation. And in interpretation, there is agency. In wonder, there is resistance to silence. Even now, in this era where the universe is still legible, we begin to build instruments not just to look, but to listen more deeply. We send spacecraft beyond the reach of our sun, messages carved in gold and digital pulses, hoping that someone, somewhere, someday, might hear and reply. Not because we expect them to, but because we can. This act of asking across impossible distances, of waiting with no assurance, is the most human kind of hope. It is not naive. It is not desperate. It is simply the echo of awareness refusing to be still. If one day, on a world we'll never see, a mind will never meet points an eye at a cooling remnant and deciphers its origin, they will find traces of us in the dust, not as conquerors, not as footnotes, but as part of the unfolding a voice that rose briefly, and spoke, and listened. before returning to the dark from which it came. Imagine a voice so ancient that it speaks not in words, but in vibrations rippling across the void. No sound touches your ears, yet the universe resounds. You are lying beneath a canopy of stars, still and silent. But overhead, reality is anything but quiet. The night sky is an active symphony, bursting with stories that traverse billions of years. It is the place where time stretches, where gravity bends, and where light becomes a messenger from forgotten epochs. Every photon from a distant star is a time traveler. When it touches your eye, you are not seeing that star as it is, but as it was 10, 100, a billion years ago. Starlight does not merely illuminate, it testifies. What you see is a fossil record in the medium of light. Yet the universe's most haunting music doesn't ride on sound waves. In the vacuum of space, traditional sound cannot travel, but the cosmos still sings. It sings in electromagnetic radiation, in gamma rays, X-rays, ultraviolet and radio waves. These signals, translated by radio telescopes, tell us of spinning neutron stars, the collapse of suns, and the faint hum of the infant universe itself. You are in the control room now. Massive radio dishes point to the sky. On the monitors, rhythmic pulses appear. These are pulsars, neutron stars spinning hundreds of times per second, each one the collapsed core of a supernova. They emit radiation with such perfect timing that we use them to keep our atomic clocks in check. The death of a star becomes the heartbeat of our civilization's measurements. Then there are the irregular voices, bursts of radio waves from quasars, from the twisted space-time near black holes, from the explosive births and deaths of stars. Some are steady, others are frantic. Each tells of extreme gravity, magnetic storms, and matter behaving in ways we still struggle to model. One of the universe's oldest sounds is the cosmic microwave background, faint radiation emitted just 380,000 years after the Big Bang. It pervades the universe, a leftover glow from a time before stars, before galaxies, before elements as we know them. It is the cosmic echo of the universe becoming transparent for the first time. Listen closer. Hydrogen, the most abundant element, speaks too. When it flips its electron's spin, it emits radio waves at a very specific frequency. With this, we map galaxies. We see where stars are born. We trace spiral arms. Interstellar gas clouds are not silent. They tell us where new suns will blaze into being. And our own star, the sun, is a wild instrument. It flares, it storms, it disrupts satellites and sparks auroras. It sends out coronal mass ejections, billion-ton clouds of plasma that can knock out power grids. It hums with activity beneath its surface, vibrating in oscillation modes we can detect. None of this is chaos. It is symphony. Patterns within patterns. Harmonies buried in noise. Chaos becomes data. Data becomes meaning. And yet, among all these signals, we hear whispers of something more enigmatic, something we cannot see but whose influence is overwhelming. Galaxies spin faster than they should. Light bends more than expected. A hidden force holds galaxies together. We call it dark matter. Dark matter is not just an absence, it is a presence without visibility. It neither emits nor absorbs light, but it has mass. It has gravity. It shapes the universe. In the 1970s, Vera Rubin noticed stars orbiting galaxies too quickly. They should have been flung into space, but they weren't. Something invisible kept them bound. That something, dark matter, makes up about 27% of the universe. We only see the scaffolding it creates. Imagine a dance, with visible stars and gas swirling around a phantom partner. The dancers move to music we cannot hear, led by something that eludes all senses but gravity. We map this dark matter by observing how it bends light, a process called gravitational lensing. Light from distant galaxies is curved, magnified, and split by mass we cannot detect, as if space-time itself is a warped mirror. There are theories. WIMPs, weakly interacting massive particles, are one candidate. These particles might pass through your body by the billions every second, unnoticed. Or maybe it's axions, exotic low-mass particles. Or perhaps it's not particles at all, but tiny primordial black holes born in the earliest seconds after the Big Bang. Underground detectors wait in stillness. They sit deep in old mines or under mountains, shielded from cosmic rays, waiting for a single particle of dark matter to collide with a nucleus and leave a trace. So far, silence. But silence in science is not failure. It is patience. It is readiness. It is knowing that absence can speak. The search continues. Each non-detection is a refinement, a narrowed path through the thickets of theory. And above, the stars go on spinning. Galaxies keep their form. The unseen hand persists, as if space itself remembers a shape we cannot yet recognize. Meanwhile, we move toward the most extreme place known to physics, the black hole. Born from the death of massive stars, black holes are regions of such density that space-time caves in on itself. A singularity lies at their core: infinite density. Zero volume. Around this point is the event horizon, the boundary beyond which nothing returns. Time behaves strangely near a black hole. To an outside observer, anything falling in seems to slow, to freeze. But for the falling object, time ticks as usual. Cross the event horizon, and all paths lead inward. Some black holes are stellar mass, formed from collapsed stars. Others are giants, millions to billions of solar masses lurking at the centers of galaxies. Sagittarius A, the supermassive black hole at the heart of the Milky Way, anchors our galaxy. Our solar system orbits it every 230 million years. In 2019, we saw the silhouette of a black hole for the first time. Not directly, but by imaging its glowing accretion disk matter spiraling in, heating to billions of degrees. The Event Horizon Telescope, a global array of radio observatories, gave us a picture of the M87 black hole, a bright ring around a shadow. And black holes do not live forever. Stephen Hawking predicted they emit faint radiation. Hawking radiation due to quantum effects. Over immense timescales, they will evaporate. The cosmos will grow dimmer, quieter. But not yet. Not today. For now, the universe still roars, even in its darkest corners. The distant moon hung low over the Martian horizon, a pale sliver against the rust-red dust. As the first explorers set their instruments in the soil, here, at the boundary of Earth's influence, a new perspective began to form. Beneath the planet's thin sky, stripped of a protective magnetosphere, the silence was not just auditory, it was existential. This was not Earth extended. It was something else, something wholly alien. The dust underfoot had not shifted for millions of years. Each grain was a relic, untouched by rain or running water, shaped only by the breath of thin winds and ancient impacts. And yet, in this stillness, a new kind of motion was born, not of rock or weather, but of thought. What would it mean to build a human presence on Mars? Could our minds, wired for forests and oceans, adapt to crimson plains and twin moons? The cosmos is not built to accommodate human need, but neither is it hostile in any deliberate way. It is indifferent, and in that indifference, there is a peculiar freedom. Mars, though often imagined as a dry, frozen desert, tells a richer tale. Evidence of past rivers, of ancient lakes, even of possible oceans, lies in the sinuous channels etched into its surface. Clay deposits, which only form in the presence of water, whisper of epochs when Mars was blue. And if it once held water, could it have once held life? The question is not trivial. It pushes against the boundaries of biology. Life, we now know, can exist in boiling sulfur springs, in the vacuum of space, in clouds of acid. Why not in the subterranean aquifers of an ancient Mars? To search for life is to search for connection, not merely in the microbial sense, but in the recognition that we are not a singular cosmic accident. If life emerged independently on Mars, even once, it would mean the universe is fundamentally inclined toward complexity, toward pattern, toward awareness. From orbit, Mars reveals scars of cataclysm volcanoes like Olympus Mons, the tallest in the solar system, and Valles Marineris, a canyon system that dwarfs Earth's Grand Canyon. These formations speak of forces vast and violent. They also remind us that Mars is not dead. It slumbers. Seismic activity and strange methane emissions hint at processes still ongoing beneath its crust. Perhaps it is not a world frozen in time, but one caught mid-transition. The journey beyond Mars takes us into realms of scale that bend comprehension. Past the asteroid belt, where Ceres, a dwarf planet, lurks as a forgotten embryo of planetary formation, we enter the realm of the gas giants. Jupiter, with its churning bands of storm and radiation belts, guards the solar system like a gatekeeper. Its gravity shapes the orbits of comets, shepherds asteroids, and may have shielded Earth from countless impacts. Yet it is not just a protector. Within its orbiting moons lie some of the most promising places to search for life beyond Earth. Europa, with its cracked icy shell, likely hides a liquid ocean beneath, warmed by tidal flexing. Ganymede, the largest moon in the solar system, possesses a magnetic field and anomaly among moons and hints at subsurface oceans of its own. Saturn's Enceladus ejects plumes of salty water and organic molecules from geysers near its south pole. These are not dead rocks. They are worlds in waiting. Each of these icy bodies challenges our terrestrial assumptions. On Earth, life clings to thermal vents on the ocean floor, independent of sunlight. Might similar ecosystems thrive in the dark seas of Europa or Enceladus? If so, the universe might teem with biology not in Earth-like temperate zones, but beneath frozen shells, in the warmth of tidal embrace. Uranus and Neptune, the ice giants, bring new mysteries. Their atmospheres swirl with exotic chemistry, and their magnetic fields tilt wildly from their rotational axes. Neptune's moon. Triton orbits backward, a clue to its captured origin, and geysers of nitrogen vent from its crust. These outer worlds are not merely far, they are strange in ways that challenge both instruments and imagination. Beyond them lies the Kuiper Belt, a realm of frozen remnants, including Pluto, whose demotion from planetary status obscures its intricate geology and possible internal ocean. The New Horizons mission revealed a heart-shaped basin of nitrogen ice and mountains of water rock. Even here, at the edge of sunlight, geology speaks. And then, at last, the heliopause, the boundary where the solar wind yields to the interstellar medium. Voyager 1 crossed it in 2012, becoming the first human-made object to enter interstellar space. Its golden record, bearing music and messages from Earth, floats onward into the dark, a whisper of sentience hurled into the abyss. What does it mean to extend our senses so far? To know, with certainty, that we have sent artifacts and perhaps soon, people beyond the nursery of Earth. It is not conquest, it is communion. The search for alignment with forces larger than ourselves. The impulse is not to dominate, but to understand. In the silence beyond planets, where only photons and particles drift, our thoughts continue. About time, about death, about continuity. When we plant a flag or a sensor, it is not to say we own this, but to declare we noticed. It is a profoundly humble act. The solar system is a cathedral of time and physics. Each moon, each orbit, each cratered surface is a chapter in a book older than humanity. And we, with our instruments and questions and dreams, are its youngest readers. But beyond reading, we may someday write, leave traces not only of biology, but of poetry, logic, compassion, a lander's medal, a rover's track, a human footprint pressed into Martian soil, not noise, but meaning. In the faint light of a distant sun, the first greenhouse might bloom, the first cry might echo in a dome, not as colonizers, but as participants in a story that is still being told. Imagine drifting through the frozen edge of our solar system, past the orbits of Neptune and Pluto, into the Kuiper Belt, where icy relics from the birth of the sun still orbit in their ancient paths. Here lie the dwarf planets, comets, and countless icy rocks that whisper of a primordial time. It is a silent realm, barely touched by sunlight, where time seems to stretch and celestial mechanics dance in slow motion. As you pass through, your gaze is drawn toward the mysterious Oort cloud, a hypothetical shell of icy objects far beyond the planets, stretching halfway to the nearest stars. If a comet begins its long journey toward the sun, it may have originated here, perturbed by the gravity of a passing star or a ripple in the galactic tide. The outermost reaches of our solar system mark the boundary between the known and the speculative. This is where gravitational dominion gives way to interstellar drift. Out here, the solar wind fades, and the heliopause, our sun's final breath, meets the interstellar medium. Beyond this invisible threshold lies the vast ocean of the galaxy, populated by rogue planets, errant comets, and the interstellar gas from which stars are born. Each particle of dust out here is a relic older than any terrestrial stone, untouched since the galaxy's youth. Our journey now moves inward, not in space, but in scale. We dive beneath the surface of understanding, into the infinitesimal heart of matter. Everything you see, touch, and know is made of atoms, billions of them dancing in patterns too small to perceive. Each atom contains a nucleus, a dense core of protons and neutrons, surrounded by a ghostly cloud of electrons. But even these subatomic particles are not fundamental. Inside protons and neutrons reside quarks, held together by gluons in a dynamic tension described by quantum chromodynamics. Quarks, electrons, neutrinos. These are the building blocks of the universe, governed by the rules of the standard model of particle physics. It is our most successful framework for understanding matter and its interactions. Yet, it is also incomplete. It says nothing of gravity, of dark matter, or of the strange imbalance between matter and antimatter. Physicists search for unification, a deeper layer of reality where all forces merge, where the universe writes its rules in simpler terms. To probe this hidden structure, scientists use colossal machines, particle accelerators like the Large Hadron Collider. These vast rings hurl particles to near light speed and smash them together, recreating conditions just moments after the Big Bang. From the debris of these collisions, we discovered the Higgs boson, a particle that gives mass to others through a field that permeates all of space. It is like an invisible molasses through which everything must pass. But even the Higgs, profound as it is, does not answer every question. What stabilizes the mass of the Higgs itself? Could supersymmetry provide the answer, positing partner particles for every known one? Or might string theory hold the key, suggesting that all particles are different vibrations of tiny strings existing in 10 or 11 dimensions? These ideas remain unproven, beautiful, but elusive. The closer we look, the more the universe begins to resemble a question. Is space-time itself granular, made of discrete units smaller than any atom? Some physicists believe in loop quantum gravity, a model where space and time emerge from networks of interconnections, quantum threads woven into the cosmos. Others ponder the holographic principle, which suggests that everything we experience in 3 dimensions is encoded on a distant 2-dimensional surface, like a cosmic projection. And what of time? Is it an arrow, always pointing forward, or an illusion born from entropy? The laws of physics are mostly time-symmetric. They work just as well in reverse. Yet, our experience of time is not symmetric. We remember the past, not the future. Entropy, the measure of disorder, increases. This is the one true direction time seems to follow. But why did the universe begin in a state of such low entropy? Why was it so ordered at its birth? Perhaps the most profound mysteries lie not in the stars, but in the silent intervals between them, in the gaps of our knowledge, in the stillness where science meets philosophy. The cosmos is not just a place of planets and particles. It is a stage where meaning, consciousness, and curiosity come to life. We, the observers, are also part of the experiment. As we float back from the microscopic into the vastness again, we carry with us the recognition that we are not separate from the universe, we are of it. Each atom in your body was forged in the heart of a star. Each breath echoes cycles of carbon and oxygen that have danced through 1,000 forms. The universe dreams through us, and in contemplating it, we allow it to know itself. The edge of the solar system, the edge of matter, the edge of certainty. These are not limits, but invitations, reminders that exploration begins when we dare to ask the questions that have no easy answers. 100,000 light-years from end to end. The Milky Way is a structure vast enough to contain billions of stories, and yet it is only one galaxy among countless others. Its spiral arms hold a history of cosmic birth, violence, and evolution. But even in its grand design, our vantage point remains constrained. We look from the inside out, our solar system nestled in one quiet fold of the Orion Arm, orbiting the galactic center like a boat gently circling the eye of a storm. The stars above seem eternal, yet they too move, pulled by invisible currents, sculpted by forces we cannot touch. Each one participates in a vast celestial choreography. It takes the Sun 230 million years to complete just one galactic orbit. In that time, entire species have risen and vanished on Earth. The dinosaurs lived and died without completing a single cosmic lap. Now, under the night sky, we follow their path with radio telescopes and digital star charts. Beyond the spiral arms lie stellar halos and globular clusters, ancient, spherical groupings of stars orbiting the galaxy like bees around a hive. These clusters are fossils, containing stars almost as old as the universe itself. Studying them is like peering into a cosmic archive, unlocking information about the galaxy's adolescence. Their orbits are wild and elliptical, often slicing through the galactic disk. Their presence hints at collisions, past galactic mergers that left behind structural echoes. We now know the Milky Way is on a slow, inevitable collision course with the Andromeda Galaxy. In roughly 4.5 billion years, the two spirals will begin to interact. Their stars will mostly pass without colliding, like dust motes blown through one another. But gravity will stretch and warp the galaxies into streamers of stars. The final product will be an elliptical galaxy, swollen and slow. Some call it Milkomeda. It will be a new home for old stars. But galaxies aren't just stellar cities. They are governed by dark matter halos invisible, massive envelopes that dictate the galaxy's structure and motion. These halos are not decorative. They are architectural. Without them, spiral arms would fly apart. The visible galaxy is just the skin of a much deeper, invisible anatomy. Within this scaffolding, gravity sculpts matter into patterns and forms that are replicated across the cosmos. These structures form filaments, walls, and voids the cosmic web. On the grandest scale, the universe resembles a neural network, with galaxies as nodes connected by filaments of dark matter and gas. Between these filaments lie immense voids, where few galaxies dwell. These are the deserts of the cosmos, vast stretches of near-nothingness. If you could step back far enough to see the web in full, you might feel as if you were gazing at a living organism. Yet this structure is dynamic. Superclusters slowly drift, galaxy clusters merge, and quasars, supermassive black holes at galactic cores, send jets of particles through intergalactic space. These active galactic nuclei are among the brightest phenomena in the universe. They burn with energy drawn from the innermost orbits of matter, spiraling toward gravitational oblivion. Their light travels billions of years to reach us, a testament to power born from collapse. Instruments like the James Webb Space Telescope now peer into these deep structures, capturing light from the earliest galaxies. It sees not just the glow of stars, but the spectral fingerprints of their composition: oxygen, carbon, even water vapor in nascent planetary systems. We are watching the universe watch itself become. In this light, we begin to glimpse not only what the cosmos is, but what it has the potential to be. As we trace these immense structures, the arrow of time continues its slow cosmic march. Thermodynamics tells us that entropy increases, order becomes disorder. Galaxies will eventually run out of fuel, their stars dimming, their matter decaying. But the story doesn't end with extinction. Matter that once formed stars and life will disperse, contributing to new structures. Nothing is wasted in the cosmos, everything transforms. On some distant day, when the last star flickers out and black holes begin their long evaporation via Hawking radiation, the universe may reach a state of maximum entropy, a diffuse, dark sea of particles and fading remnants. But even then, the laws of physics persist, whispering through silence. The universe remembers its origins not in memory, but in structure. And yet, across this vastness, the spark of inquiry continues. From a small blue planet on the edge of a minor spiral arm, consciousness has risen that dares to ask where it came from and what might lie ahead. We are not mere observers. We are participants in a universe still in the act of becoming. The Earth rotates slowly beneath a sky full of secrets, and as dawn begins to stain the horizon with soft light, the final frontier we've been tracing reveals yet another boundary, not of matter, nor of space, but of understanding itself. Human cognition, our curiosity, our fears, our models is the last telescope we aim outward and inward. In the midst of distant galaxies and decaying stars, the very idea of intelligence demands attention. Intelligence is not just a feature of biology, it may be an emergent property of matter, given time, complexity, and the right constraints. Earth may be a proof of concept, but if minds can emerge here, why not elsewhere? Could galaxies be learning systems? Could consciousness, somehow, be entangled with cosmology itself? We usually think of intelligence as a late evolutionary development, a tool for navigation, tool-making, storytelling. But consider the possibility that intelligence is also a cosmic phenomenon, an entropy negotiator, a meaning maker in an otherwise indifferent expanse. Some physicists speculate that life, and perhaps intelligence, could serve as a counterbalance to entropy, shaping order even as the universe trends toward thermal equilibrium. In this framework, every self-aware being becomes a node of resistance, a flicker of coherence against the pull of chaos. And every question we ask about the universe is the universe, in a sense, asking itself. Now imagine a future where intelligence becomes not just biological but cosmic in scale. Civilizations, if they survive their infancy, may begin reshaping not just planets, but stars. Dyson spheres, hypothetical megastructures encasing stars to capture their full energy output, are one example. We haven't detected any yet, but our searches for Type 2 civilizations, those capable of harvesting the energy of entire stars, or Type 3 civilizations that manipulate galaxies, continue. If they exist, they're subtle, or they've transcended detectable physicality altogether. Perhaps intelligence eventually merges with space-time structure, embedding itself as information gradients, quantum echoes, gravitational imprints. And if civilizations collapse as ours might, they still leave behind artifacts of thought, radio waves sent eons ago, gravitational lensing patterns from abandoned stellar engines, the final memory of a thinking species encoded in the rotation of a neutron star. But even if we are alone, uniquely aware in an otherwise quiet cosmos, our awareness may be enough. To observe the universe is to become part of its unfolding. Just as measurement changes the state of a quantum system, consciousness alters the narrative trajectory of the cosmos. And what of the end? What awaits when the stars burn out, when black holes evaporate, when entropy finishes its slow, patient erasure? The far future of the universe is an austere place, cold, dark, sparse, but some speculate that information might never be entirely lost. The universe, even in its final state, could remain a container of memory. Through theories like the holographic principle, where the three-dimensional world is described by two-dimensional information at its boundary, we begin to glimpse a reality where space, time, and matter are all emergent properties of deeper informational structures. Some go further still, proposing that the universe itself is a kind of computation, not metaphorically, but literally a quantum process unfolding across dimensions. From this perspective, our thoughts, our dreams, our efforts to understand the stars are operations in a grander algorithm whose purpose we may never decode. Still, we calculate, we remember, we imagine. And imagination is no small thing. It is the propulsion of science, the architecture of empathy, the poetry of discovery. Through imagination, we transcend the here and now, projecting ourselves into alien atmospheres, lost epochs, and speculative futures. As we continue this cosmic journey, we must also face the mirror. The tools of astronomy, cosmology, and particle physics have given us unprecedented power but also deep responsibility. What we do with this knowledge will shape not just our destiny, but the future of sentient matter in this corner of the universe. How we handle climate instability, resource depletion, artificial intelligence, and our interdependence with ecosystems will determine if we're a long-lived civilization or a brief spark in galactic time. The stars will go on, but whether we remain to witness them is not guaranteed. Even the act of looking up, so simple, so ancient, is a form of hope. It says, there is more than this moment. There is more than ourselves. It acknowledges both our fragility and our vast potential, and it affirms that wonder is still the most honest response to existence. So, when you next lie beneath the open sky, remember you are a participant in the most complex, most beautiful, most mysterious story ever told. A story still being written, a journey still unfolding. And the stars. They are not just lights in the sky. They are questions, waiting for minds to ask them.